We're always told to look at the average, the mean, that one number that's supposed to tell us everything. But what if focusing on just the average is actually making us miss the most important part of the story? Today, we're going beyond that middle number to talk about something that's often way more important: consistency, or as the statisticians call it, variance.
So let me just ask you straight up, is the average really all that matters? Think about it. If you're managing a factory, waiting for your bus, or even just trying to get better at something, the answer is absolutely not. It's the spread, the wobble, the inconsistency around that average. That's where the real action is. All right, so here's how we're going to tackle this. First, we'll see exactly why averages can be a problem. Then we'll get our hands on a cool tool called Chi-Square to measure that wobble. We'll figure out how to find a likely range for it, put a claim to the test, and even compare two different options. And finally, we'll see why, in so many situations, consistency really is king.
Okay, let's dive right in. Section 1, the problem with averages. To really get why this matters so much, we're going to start with a super simple real-world example that shows you why that middle number just isn't enough.
So picture a factory that's filling up bottles of liquid detergent. Now, both of these production lines, process A and process B, have a perfect average fill of 16 ounces. But just look at them. Process A is beautiful, it's consistent, it's reliable. Process B, on the other hand, is a total mess. You're wasting money overfilling some bottles, and you're ripping off customers by underfilling others. The average is technically correct, but the inconsistency, it's causing massive problems. And this wobble, this inconsistency, it actually has a formal name. We call it variance. It's just a number that tells you how spread out everything is. A nice, low variance, like our process A, means everything is tightly packed around the average, predictable. A high variance, like that chaotic process B, means your results are all over the place.
So how do we actually get a handle on this variance? I mean, we can't just guess. We need a proper tool for the job. And that brings us to our new best friend, the chi-square distribution. Now, don't let the fancy Greek letter throw you off. Seriously, just think of chi-square as a specialized ruler. It's designed to do one job and one job only: measure variance. It's what lets us take a small sample of something and make a really smart guess about the consistency of the entire system. Let's put this ruler to work. The first thing we can do is answer a question every manager has. Okay, I get it, my process isn't perfect, but just how inconsistent are we? We're going to find a likely range for the true underlying variance. So back to our detergent factory. They pull a sample of 20 containers off the line and measure the variance, which comes out to 0.0025. And they want to be 95% confident about their final answer. These numbers are all the ingredients we need, including this thing called degrees of freedom, which, don't worry, is just the sample size minus 1. Easy enough. We plug those ingredients into our chi-square tool, and here's what we get: a 95% confidence interval. This tells the factory managers that, even though they only tested 20 bottles, they can be 95% sure that the true variance for their entire production line is somewhere between 0.0014 and 0.0053. And just like that, a vague feeling about inconsistency becomes a hard, measurable range they can actually work with. Finding a range is super useful, but what if you have a specific target you need to hit? What if a company claims they meet a certain quality standard? Well, now we have to go from estimating to testing. We need to run a hypothesis test. Let's take the St. Louis Metro Bus Company. They have a rule. The variance in their bus arrival times can't be more than 4 minutes. We want to see if they're actually failing to meet that standard. The easiest way to think about this is like a courtroom. The null hypothesis is the assumption of innocence. We assume their variance is fine. The alternative hypothesis is what we're trying to prove, that they're guilty of being too inconsistent. And the process is always the same, nice and simple. Step 1, we just did that. We stated our hypotheses. Next, we're going to grab some data on bus arrivals and calculate a test statistic. Then we find our critical value. You can think of that as the line in the sand our evidence has to cross. And finally, we just compare the two and make our call. And here it is, the evidence. Based on a sample of 24 bus arrivals, our test statistic comes out to 28.18. Now remember that line in the sand we have to cross to prove they're too inconsistent? That's our critical value. In this case, it's 35.172. So the question is, did our evidence beat that threshold? So what's the verdict? Well, 28.18 is less than 35.172.
Our evidence didn't cross the line. So in fancy stats talk, we failed to reject the null hypothesis. What that really means in plain English is that we just don't have enough evidence from this sample to say the bus company is failing. For now, they remain innocent. Okay, that's how you test one company or one process. But what happens when you have to compare two different things? Like maybe you're choosing between two suppliers or two different machines. For that, we need a different tool. It's time for the F-test.
Let's check out Dulles County. They need to hire a school bus company, and for them, reliability is everything. So they run a little test, and they measure the arrival time variance for two bidders, Milbank and Gulf Park. And from the samples, it looks like Milbank has a much higher variance, 48, compared to Gulf Park's 20. But here's the million-dollar question. Is that a real difference, or do we just get unlucky with our samples?
You know the drill by now. We set up our hypotheses. The null hypothesis, our default assumption, is that there's no real difference in consistency. They're basically the same. The alternative hypothesis is what we're checking for, that there is a real statistically significant difference in how reliable they are.
So how do we decide? Well, we calculate our F-test statistic, which is just the bigger sample variance divided by the smaller one. That gives us 2.40. Our critical value, our new line in the sand, is 2.28. And look at that. Our calculated value of 2.40 is bigger than the threshold. So we get to reject the null hypothesis. This means the difference is real. There's a statistically significant difference, and Gulf Park is definitely the more consistent, reliable choice.
So let's wrap this all up. As we've seen, looking past that simple average isn't just some boring math exercise. It has massive real-world impacts on quality, on reliability, and on making the right decision. So here it is, your new toolkit for understanding consistency. You've got variance itself, the main idea. You've got the chi-square test for when you're looking at just one group, either to get a range or test a claim. And you've got the F-test for when you need to compare two groups head-to-head. Each tool has a very specific and very powerful job.
And that really is the key takeaway. The next time you see an average presented as the whole story, I want you to stop and ask, wait a minute, what about the variance? From the time it takes you to get to work, to a company's profit reports, to the products you buy every day, where is that hidden inconsistency impacting your world? And what could you do if you could actually measure it? Think about it.